So the goals of this project were essentially to try and understand this maze solving agent, which is a more complex version of the, I'm not sure, let me start from the beginning. So the PropGen environment is designed for procedurally generated RL environments. And this is useful because it means that the system has to learn very general policies for solving and getting high reward in this environment. And there was some previous work that was done on this environment called the maze environment, which is over here. So you can see the maze on the left and our environment on the right. And so the maze environment is very simple in that there's a single objective, and the maze, the agent just has to navigate the maze and get to it. And our heist environment is a simpler maze, but it also has to complete multiple goals in order to reach the final objective. And our intention was to try and figure out, how does the agent go about choosing which goals to try and pursue? And is it possible that there are interesting work here in terms of how goals are actually represented within the network? Moreover, if we could try and retarget these goals and get interesting controllable behavior out of the model, we felt this would be a really cool result. So PropGen Heist is great because there's multiple goals, and it's simple enough and has existing work around it that we can reuse. And that meant that we didn't have to spend months and months rebuilding all the tooling. We could adapt it for our purposes. So yeah, what's important to understand with the heist environment is that there's roughly 4 levels of difficulty. There's, as you can see here, there's one environment or one type where there's just the gem. And then there's more difficult environments where you have the gem and blue key and a blue lock, and all the way up until level 4, where you have blue key and then a green key and a red key. And then it can finally go to the gem. So here's an illustration of how this looks. So level 1, it just goes straight to the gem. And then level 2, it has to get the blue key and unlock the door, etc. Pretty straightforward. So what's noteworthy here is that it always follows the exact same order. So it's always blue first and red last. And this is quite important for how it learns to navigate the maze. So the model architecture we were using to try and do our interpretability work on here is called the Impala architecture. And it's essentially a 15-layer CNN with a dense layer at the end. And you can kind of see how it's structured here. So it has residual blocks, which allow for some skip connections so that this just helps it learn a bit more smoothly. And a lot of the work that we did focused on the convolutional layers. And then as we got further into the project, we started to focus more on the dense layers right at the end to see if we could try and figure out how it is making key decisions with all of the information extracted from the convolutional layers. So this kind of gives you an idea. So it's a bit of a misnomer to say 0, 1, and 2, but these are essentially the blocks, of which there are 5 each. And you can see how the information becomes more compressed as we progress through the network, with the 0th layer being very simple, very close to the original input, and the final or the later convolutional layers being very noisy and being smaller in terms of total number of pixels. So this is kind of what it looks like when you have the actual observation and then how it maps into the environment. So you can see on the far left, you've got the player and the blue key and the green key. And you can see how different filters within the different convolutional layers pick up on the different parts of this environment. So some are very focused on the walls and pay less attention to the objectives. And you can see some layers specifically target certain objectives. So for example, filter 20 only really looks at the green key. And some of these layers only identify the player. So for example, 10, 11, and 12 don't really highlight the key locations very much, but they highlight the player. So we wanted to try and understand if there was like specific filters that we could try and identify that had strong control over the outcomes or decisions of the network. We didn't end up actually creating this fantastic map of this quite yet, but this is like future work that we're still in the process of developing. So let's talk about what we actually want to understand here. So what is the hierarchy of goals that the model wishes to pursue? What algorithm does the model use to navigate the maze? And at what point is the model's current goal actually chosen? So I think we made the most progress on the final question here. We still have some room, especially on the second question. And the first one, we have a fairly good idea of how it actually tries to solve, or what order it tries to solve the maze in. And we'll get into that as we go on. So a big part of our work was focused around building probes that actually tried to extract where certain key decisions were being made within the network. So one way of doing this is to use a set of data sets that we built to represent specific situations, and these situations mapped quite closely onto the different states of the environment. So one such state is where there's only a gem, another is where there's a blue key and it needs to take the blue key and move forward. Other states would be where there's just a blue lock and it needs to go through there in order to get to the gem. And so these are the different classes that were built to try and extract how the network was representing these categories. So yeah, you have them all there. And so our main, or one of our focuses here was training these probes on the hidden dense layer right at the end of the network on these objective categories. And so you can see that it has fairly accurate results, especially for the most common and yeah, the class that's probably the most important, which is the gem, which it will always have to deal with. And then you can see the accuracy kind of gets lower as it sees the more rare objectives within the environment. So the red key and the red lock, which show up the least in the distribution of mazes. So what this kind of tells us is that the model is clearly able to identify what it's dealing with and what kind of state it's in. But yeah, we think that in order to get higher results on this, it might be a matter of training the model for longer, because we were kind of just training the model ourselves and we didn't have nearly as many GPUs handy as OpenAI did when they trained these models. So we think that this might be something that will improve if we had a lot more compute available. This is just a confusion matrix to represent where a lot of confusion tends to happen. So as you can see, there are a lot of color mismatches. So it would often confuse the red key with the red lock, as well as like the blue key and the green key. And so it's fairly understandable, but yeah, we generally have like quite a good set of representations within the final dense layer here. Now, to show that to compare this to a later layer, which we anticipate would have more difficult to extract representations, this is the layer after the hidden, and we call this the largest FC. And this had much, much lower accuracy on the probes. So you see the best it sort of got was about 35%. And this isn't that much better than random guessing, but it does show that there's some understanding, but that it's much less clear than in the larger dense layer. Another thing we wanted to try and figure out was how direction and choices around which part of the maze it would be exploring would be determined. So in order to figure this out, we built a simple directional data set, which just basically captures which corner of the maze is the gem in. And as you can see, you've got top right, bottom right, bottom left, etc. And this obviously would vary depending on the specific maze that we're dealing with. But yeah, in this case, we found that it had exceptionally good results, but this was an incredibly easy data set for it to do well in. So we think that there might be issues with this particular approach to finding out the direction. And we think a more challenging structure to this data set would probably yield a much better result. You can also see that when we trained this on the logits layer, it had quite high accuracies, but yeah, still a significant drop off in the hidden layer. Then another approach we wanted to try out was if we could engineer specific behavior using activations that we could quite accurately pull out from the model. So in this case, we wanted to figure out if we could take the gem activation and have the model try and solve the environment and then ignore the gem. In this case, what we generally saw was that, well, I'll show you so a little GIF. So on the left, we have the model with the activation steering being applied. So what we're doing here is we are taking the two samples, one with the gem and one without, and then we are minusing them to get the diff, which gives us the specific gem activation. And then we take that gem activation and we minus it, we minus it from the specific activations at a layer roughly in the middle of the network. And it didn't give us exactly the result we wanted, but it does disturb models' performance pretty profoundly. So instead of going and getting the key and like trying to solve the environment at all, it gets a bit stuck in the middle. But we think this approach might work. It seemed to work extremely well in the maze exploration in the earlier work, but this is probably a bit confusing because there's a lot of overlap between the different objectives, and it doesn't seem able to recover from the disruption. Cool. So Narmeen, can you take over from here?